Hello and welcome back. So, in the previous lecture we were looking at the first law of thermodynamics, where we saw that work and heat are both in some sense forms of energy in transfer, and we saw that for a cyclic process the net work done and the net heat transfer are equal if you find out these values in SI units. And we saw the difference between the heat transferred and the work done is essentially something we call as the change in energy. So, in some sense what we see is that work and heat are ways in which we can put in energy into a system or take energy out of the system, and they are different. We will at some later point in the course, when we look at the second law, see how they are different. But in the meantime, in order to look at real systems, in addition to knowing the first law and how to find out the work and heat, we also need to know what the properties of substances are like. So, that is essentially what we are going to look at today. So, we are going to look at properties of what is called as a pure substance. So, this means that we first need to know what a pure substance is, and this is essentially how we define it. A pure substance is a substance which has uniform composition as well as chemical aggregation throughout the process under consideration. So, we are looking at composition, we are looking at chemical aggregation, but we are only going to look at it as far as our process under consideration is concerned. So, for example, if we have some process going from some point 1 to some point 2 on, let us say, a PV diagram, some process of this kind, then all we are interested in is about the composition and chemical aggregation during this process. We are not concerned about what the substance is when it is not being used for this process. So, what we decided or discussed earlier is that the system has different states, and the states are defined based on the number of properties which we have. We said that the properties can be, for example, pressure and volume and temperature. It can also be energy, enthalpy and so on. But how many properties we need is something which we did not clearly say at that time. That is because we need to consider what kind of substance it is before we can say how many properties are required. So, the number of properties needed to define the state uniquely depends on the type of substance which constitutes the system. So, for example, if we have a chemically reacting system, we have, like, say, methane which is being burnt in oxygen to form carbon dioxide and water, we would need a certain number of properties. If it is a falling body, if I have, for example, this mouse over here, let us say it is falling, I would need a certain number of properties, because I would need to know, for example, its temperature. I would also need to know its velocity. I would need to know how far away it is from the surface, because that will tell me something about its potential energy and so on. So, the kind of system it is and what kind of process it is undergoing tells me how many properties I need to know. So, but before we discuss about the number in a little more detail, we can see whether we understand what we mean by a pure substance. So, for example, is air a pure substance? So, you should possibly pause here and think about it for a moment. So, air is made up primarily of nitrogen and oxygen. It is mostly nitrogen, about 76% or so of nitrogen, and we have about 23% of oxygen, and then we have other constituents such as water vapor and carbon dioxide and so on. So, the question is it a pure substance? So, if we look at it in rigorously in detail, so what we would see is, if I considered air at, say, room temperature and atmospheric pressure, it is a mixture of these. For simplicity, maybe I can consider it to be mostly nitrogen and oxygen. I can maybe even forget about the rest of these, and it is a mixture, it is uniform, the composition is uniform, it is dispersed out and so on. But supposing I now start cooling this air, I will reach some point where the oxygen will become a liquid, and then what I would be left with is, in the gaseous phase I would be left with nitrogen, and in the liquid phase I will be left with oxygen. So, clearly there the composition in the liquid phase and the composition in the gaseous phase are not going to be the same, and it would not be a pure substance. But for most practical applications, I am not really looking at such low temperatures where oxygen would have, for example, become liquid. So, for most practical applications of the kind which I am going to talk about, even though air is not completely a pure substance, it behaves like a pure substance for all practical purposes in the kind of temperature ranges I am interested in. For example, let us say I am interested in the temperatures from about 20 degrees centigrade to say about 500 degrees centigrade or so. It is going to be a mixture of nitrogen and oxygen primarily, and the properties are not going to change because it is not going to separate out into phases. So, even though it is not really a pure substance, it can be considered a pure substance for these kind of processes which take place. I have another question here. So, would you consider a combusting hydrogen and oxygen mixture a pure substance? So, what we have here is initially a mixture of hydrogen and oxygen. It starts to burn and the hydrogen and oxygen react, and if it is in the correct proportions, what I am left with after the combustion is water. So, clearly if I have a process in which this is happening, the chemical composition is changing. So, initially it is hydrogen and oxygen and later on it is replaced by water. So, this would definitely not be a pure substance. So, this would be a pure substance under certain conditions, but if I am looking at a very wide range of temperatures where, for example, I have liquefaction of one of the gases, then it would not be. This is not going to be a pure substance. And the third case I have here is when I have a mixture of steam and water. So, the question is, do we consider that to be a pure substance? So, steam is essentially water in the vapor form and I have water in the liquid form. So, I have a, let us say, a closed container, I have water vapor on top, I have liquid water at the bottom, I have nothing else in it, the container is closed, and I am considering these two as a system. What we see is some water can evaporate and become steam, steam can condense and form water, but as far as the chemical composition is concerned, nothing is changing. So, I can consider that to be a pure substance for any process which I am taking. So, when we have substances like this, what we are interested in is in finding out the properties when the system undergoes a process. So, when we have systems of this kind with a pure substance, we can use what is called as a two property rule, which is in some sense a reduction of the Gibbs phase rule, and the two property rule is stated in this form. The state of a pure substance of given mass can be specified in terms of two independent properties in the absence of effects due to gravity, motion, electricity, magnetism, elastic deformation, etc. So, I am going to underline a few more things. We are looking at a pure substance here. What we are saying is we can specify the state if we know two properties. Of course, we should know the mass. For a given mass, we can find out this state in terms of two properties, or we are looking at intensive properties, then it is all right. But these two properties need to be two independent properties, which means they cannot be dependent on each other. We will look at some kind of dependent properties maybe in the next lecture when we talk about two phase mixtures. But we can specify in terms of two properties only if we do not have these other things, where we are ignoring the effect of gravity. We are saying that the system is at rest, it is not moving. We are saying that the system has substances which do not depend on the electric field, they are not influenced by magnetic field around in case those fields are available. There is no elastic deformation, etc. So, under the absence of all of these, if we have a pure substance, it is sufficient if we know two properties. And this is something which we are going to make use of to a large extent. So, one of our goals in trying to solve problems in the tutorials as well as in the assignments is to first see if we can identify two properties which we know. Because if we know two properties, then and if we have a pure substance, then based on this rule what we can say is we know all the other properties. Because if we know two properties and we have a pure substance, we can define the state, which is a point on one of those graphs. If we can define the state, it means we know all the other properties of the substance because the state is unique. So, we need to have two independent properties and then we define the state, and then we can find out all the other properties we need, and then we can do calculations of whatever else we want to find out, such as work or heat transfer or anything else which you are interested in. So, what this two property rule is essentially assuming is that there is only one mode of energy storage, and that mode of energy storage is essentially the internal energy. So, we are saying that the system is at rest, so it is not moving, so there is no kinetic energy. The system is not moving, so potential energy is not relevant because nothing is going to change. So, if we have only one energy storage mode, which is internal energy, then two independent properties are sufficient to define its state, of course, for a given mass. So, we can think of, for example, a pure substance in a piston cylinder arrangement. So, let us say we have a piston cylinder arrangement like this. Our system is shown by the usual system boundaries. Let us say there is air in this case, where we assume that we know the composition of air and the composition is not changing and so on. Then what we can find out is that if I know, for example, the pressure and temperature, then it means I can find out and I need to know the mass. But even if I did not know the mass, using the pressure and temperature, I can find out, for example, the specific volume. These two are intensive properties. I can find out some other intensive properties such as specific volume, knowing what substance it is, as long as I can consider it to be a pure substance. Or knowing these two, I can find out, for example, the specific volume, I can find out changes in internal energy, I can find out changes in enthalpy, and I can also find out with some datum the absolute internal energy and enthalpy and so on. I can do the same thing if this was, for example, a mixture of water and steam, or if it was some other pure substance like let us say hydrogen or so on. I can find out all of these properties given two independent properties under, of course, the assumptions that this is at rest, there are no electric magnetic forces and so on. So, that kind of a substance is what we call as a pure substance, and we are often going to look at what we call as a simple compressible system, which is a system where electric magnetic forces and so on are missing, where the system is at rest, so that we do not have to worry about the kinetic energy of the system itself, and we do not have to worry about changes in potential energy either. So, we are going to often talk about simple compressible systems which contain a pure substance. So, this would be, for example, a simple compressible system containing a pure substance, and once we know that this is the case, all we need to do is know two properties, and then we can find out whatever else we need. So, what we have assumed in the previous slide is that once we know two properties, we know all the other properties, which means we are assuming that we know property relations between the various properties. So, now we look at what those property relations are and how we can get them. So, for the purpose of these property relations, based on what these relations look like, we are sort of classifying these substances into various categories. One of them is what we call as an ideal gas, where we have one substance which in the gaseous form and it behaves in some ideal fashion. We will define what that is. A second case for this course we are going to look at is what is called as a mixture of ideal gases, where we have like more than one gas, for example nitrogen and we have oxygen, and let us say we mix them together and we have a composition of those two. In a particular composition we usually call that as air, ignoring other traces of other gases. That kind of substance is something which we can deal with. A third case we can deal with is where we have one substance, in this case H2O molecules, which are in both liquid phase, which we call as water, and in vapor phase, which is what we call as steam. So, we can look at vapor and liquid mixtures of one substance. We will do this in the case of say liquid and vapor water. We may also do this in the case of say ammonia or other refrigerants, which we will look at a little later in this course. Of course, this is only a small subset of all the kind of compositions we can have and all the mixtures we can have, but for the purpose of this course we are going to sort of restrict ourselves to these kinds of properties.